Can you see my screen?
Yes, sir.
Okay. So now one thing, please tell me that when is your end SEM exam? Can anybody tell me? So that I can write it in my notebook. So when is your end SEM exam? So 22 to 20 November. Okay. So we have 2 weeks remaining, right? So now when you want to give second viva, when you want to give second viva, okay, fine, you think I'll ask later again. So now we are in encoder. So we are reading the encoder. Let's share the screen. So what I was discussing yesterday that whenever we use some sensors, we need a computer. Always we have a computer, and the sensor output always goes to computer because of reading the sensor, storing the data, and taking the necessary actions such as control action and so. So for that procedure, we need a to analog to digital converter for all the sensors, because whatever the sensor we read is the analog sensor. Now, if we think about encoder, it is a digital sensor. For if we use the encoder, we don't need to have a to D converter. Directly we can feed it to computer. Now, more what we discussed, that there are two types of encoder. One is the SAPT encoder or rotary encoder, or another is the linear encoder. Among again these two again can be divided into absolute encoder and incremental encoder. And based on the operating principle, encoder can also be divided as the optimal encoder and optical encoder and magnetic encoder. So I said that among these two, optical encoder is most popular. Now you come to a little bit of construction. So now we are reading encoder. This is basically the absolute encoder. Whatever now I am trying to discuss, it is absolute encoder. So this sensor or transducer produces a digital output in the form of binary code. Okay. So each binary code represents a unique position, angular position. You see, unique angular position means that the sensor output is in the binary number, which can be compared with the unique position. Now let's try to see the construction. So let's first see the left hand side hand drawing picture. So here we see, suppose we take one glass, okay, circle, glass circle, and we divide it into three tracks. You see there are three tracks in the circle, in one, two, three. And then let's say we darken the track such a way that initially in this position there is no darkening, so 0, 0, 0. In this position we darken here. In this position we darken second track. In this position we darken second and third both. In this position we darken first track. Nothing. In this position, we darken first and third both. In this case, and first track. In this position, first, second, third, all. Right. Now, if you see, if you think about outermost track as the LSB and innermost track as the MSB, most significant digit, and outermost track is the LSB, less significant digit. Now, you use three source of detector and three three sources and three detectors. So here I try to mention these two, that the source and the detectors. So location of the source and the detectors. So three sources of light source means the light source. Okay, three light source and three detectors. Okay, so I'll come to the construction, how the light source can be made and how the detector can be made. But for the time being, if you think that there are three light source and each light source for each track. So one track we have one light source and one detector. Another track we have one light source and another detector. Another track we have one light source and another detector. So three sources and three detectors along the same line. So now if you think that the source emits the light and detector detects the light. So if there is no darkening, all the three detectors will you will detect the light. So you will get 0, 0, 0. And then and the next, if you see there is one darkening, so the two detectors will get the light source, one detector will not get any light source. So what you will see that you have 0, 0, 1 and the next like this. So if you can convert it to the light source with the light source and the detector whether it is detecting the light or not, and based on that it is generating the voltage, and that voltage is proportional to your angular displacement. Here you see for, so how many division we made here, 8 division, 1 2 3 4 5 6 7 8. So you see one division means 45 degree. So suppose if your, it is a very crude thing, I'll come refine one. So if your location is, if your output is 0 0 0, you must say that your angular displacement is in between 0 to 45 degree. If your output is 0 0 1, you must say that your angular position is in between 45 to 90 degrees such a way. So in this way, by measuring the light by with the detector and converting into voltage, you can convert the voltage beat pattern. You can correlate the beat pattern with the angular displacement. Okay. So now if you come to this one right hand side picture, it is the same picture, but it has a 1 2 3 4 4 tracks. So you can go up to 0 to 16. So you can say in the resolution of 0 to 22.5 degrees. So if you have 0 0 0 0, you can say that it is in the displacement is in between 0 to 22.5 degrees. So now let's come to the construction. Now, any query up to this point, or everybody understood? Mm, is there any query? Okay, so let's proceed then. So, if you think about the construction, so initially you see that it consists of a disk, and disk is mounted on a shaft. Okay, so there is a disk, obviously there is a disk, and disk is mounted on a shaft or placed on a shaft, and this can rotate as per the rotating shaft and all, and it is made up of glass. Now the disc is divided into uh, a few rings. We call it as a track. Okay, and based on the resolution, the number of track is selected. Suppose you want the resolution in between 0 to 45 degree, which is a very crude resolution nobody wants. So you can go for the 3 tracks. If you want 0 to 22.5 degrees, you can go for 4 tracks. So basically, what will be the resolution with the bit? So suppose you have 3, then it is 2 to the power 3, it is 8. 360 divided by 8, that will be the resolution. Now, if you have, say, 16-bit track, okay, or 10-bit track, then see 360 divided by 2 to the power 10. Now, imagine how small resolution you can achieve, okay. So, in reality, when you use SAP encoder, it has many tracks, not 3 or 4. It can have 16 track even. Okay, so resolution will be 360 by 2 to the power 16. So for each track, there will be a light source and there will be a detector. Okay, so again, I'm coming to that light source and detector. Maybe this one, excuse me, this figure you can see. So you have a shaft, and now I am seeing the circular glass, not from the side view. So you see only a ring kind of thing, or a straight line kind of thing. See, you see this, and you have three tracks, 1, 2, 3. You have the three source of light, okay, and you have the three detectors, okay, and output is coming out from the detector. So for each track, there will be a light source, okay. The light source could be LED or IRED, okay, infrared or LED, and this light source provided with the with an integral lens. So this light source, you see some dot I gave, that means it is provided with a mechanism with a lens and an aperture. So what is the meaning of lens and aperture? It is given for the lens and aperture because you see, if you provide it with the lens and aperture, what will happen? Then light directly will be focused on the track. Otherwise, what will happen if you don't have lens and aperture mechanism? Only light it will diffuse, and the light for track 1 will go to track 2 and so on. So it will be very difficult to get the accuracy. So each light source had an lens system and an aperture, so that it can only focus to the corresponding track. And on the opposite side, at the detector, what is used? A photodiode is used. On the detector side, what is used? A photodiode is used. So left hand side, we have a light source, which is LED or IRED, and we have a lens mechanism and aperture. And right hand side also we have an aperture and then detector. So as a detector, photodiode can be used. Okay. Now, when the some portion of the disk lies between the sensor, between the source and the detector, when it is transparent, then the light source will go through the disk and it will reach to the detector, and detector will produce the electrical output. Now, if it is dark, okay, or opaque, so no light signal will go and there will be no detection, so output will be 0. So with the output, it is easy to correlate the angular position. Suppose in output we get some pattern 0, 0, 1 or 1, 1, 1, or even if it 8 tracks the 0, 1 pattern, from there it is very easy to correlate to tell that what will be the angular displacement. So here if you see that we gave the 3 tracks, but it is very rare, no encoder has having 3 tracks because resolution is very bad. Its resolution will be 45 degree. So, and it is not acceptable. But suppose we have it 10 to 12 bit, generally commercially available encoders as the 10 to 12 bit output, as I was saying. So then what will be the resolution? It will be 360 by 2 to the power 10. It will be very, very good resolution. Okay. So now tell me if you understand this. Okay. Now, is this fine? So, or I need to describe again any part of it. So please tell me. If you don't understand any part, I can describe it again. But as it is very simple, just I described once, and it seems that it will be clear to all of you. So, and you are not requesting any part to describe again. So, I hope I can proceed. Okay. So now you see as the output, what you are getting? As the output you are getting a binary number, okay, which consists of 0 and 1. Basically it is a voltage. So if 5 volt or 0 volt or something, and that can be converted in a logic, which is I'm coming this one pattern, this one, let's see. So in the 3 bit, if I say that, so 0 0 1, what we are getting? We are getting decimal 0 and angle is 0 to 45 degree. If we are getting 0 0 1, so it is 1 and 45 to 90 degree, like that. So it is very simple. So here you see that the output is converted to a binary pattern, and from the binary pattern, we realize the angular displacement. Okay. Now, there is an interesting consideration we should consider. It is a very interesting consideration. Let's see if I have this one. This one, you see. So you see that the right hand middle column, you see it is a binary code. So in the binary code, you see you have 0 0 0, next you have 0 0 1. So what is the transition? One transition. Now you have 0 0 1 and then 0 1 0. What is the transition? It is two transition, 0 to 1, 1 to 0. So and it 0 0 1 to 1 0 0, it has three transition. So if you see that in binary pattern, at each point you may have more than one transition. One transition means either 0 to 1 or 1 to 0. This may create a problem. Why? Just try to understand why it may create a problem. It is very interesting. So basically, my conclusion is we will not go with binary code, rather we will go to with the gray code, and there is some reason behind that. Okay, what is the reason? Let's see. Again, go to the first figure. Let's see this beautiful figure. Okay, so when suppose our transition is happening, suppose our transition is happening from here to here. Okay, so then how many transition is happening? White to dark, dark to white. So two transitions are happening. So now think about from the construction perspective. So when a such a glass opaque or dark is made, it is done due to with the etching process. And you see that there are in a shaft there are 10 to 12 tracks. So each track is very small, and that is done by the glass etching process. Now in the construction, it is highly possible that this demarcation line is not a single line. What I mean to say, due to little bit here and there in the construction process, this dark goes slightly here, and may this dark may come slightly here. So what I am saying, instead of if it is say, if it is 1 1 0, okay, and then it is 1 0 0. So if it goes little bit here and this dark comes little bit here, then here the transition will happen, and then again here the another transition will happen. So there will be the two transition. So what will be the two transition? It will be 1 1 0 to 1 1 1, then 1, then 1 1 1, then 1 0 1. So two unnecessary transition is happening, and which will force you to 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 say that the angular deflection is other than what is the actual deflection. Are you getting it? So again, if you want, I can tell it again. So the binary code, in binary code, when you move, there might be more than one transition at any point. So in this figure, you can see that whatever I say that there is one transition. Now, earlier we have assumed that the alignment of opaque and transparent of all the tracks are perfect. Okay. Suppose three tracks we assume that alignment is perfect. There is single line before which it is always transition is happening. Means that the transition from an opaque area to a transparent area or vice versa must occur simultaneously to all the tracks. That is our assumption. So what is our assumption? Our assumption is that the transition from opaque to dark or dark to opaque, sorry, transition from transparent to dark or transparent to opaque or vice versa is happening on a single line, single transition line. But suppose if you have a three tracks, three transitions are happening simultaneously. Okay. So however, due to the limitation associated with the manufacturing process, a small misalignment can happen. That means, say track 1 has the transition earlier than the track 2, slightly earlier than the track 2. So what will happen? This is called the misalignment. So for if misalignment occurs, then you will see the bit pattern is changing drastically different if you use the binary code. But instead of that, if you use the gray code and misalignment happen, there is no disadvantage or risk, because in gray code always single misalignment will happen. Sorry, single transition will happen from 0 to 1. And if it happens little bit earlier, there is no as such no harm. It will not saying you to tell that the angular displacement is drastically different than the others. For example, if you have the pattern, say from binary code, so you from gray code, say you are going 0 1 1 for binary code 0 1 1 to 1 0 0. Let's say the misalignment is happening. So instead of 0 1 1 to 1 0 0, 0 1 1 to 1 0 0, it can happen 0 1 1 1 1 1, then 1 0 0. So two misalignments. So then if 1 1 1 is coming, you will say that the angle is drastically different and the error is huge. So it will give very gross error. So the conclusion is that these difficulties of misalignment can be solved by using the gray code instead of the binary code. So the main takeaway is in the encoder, we always use the gray code, not the binary code, to get rid of the misalignment problem, which I discussed earlier. So now tell me if you have any query in this. Or do you understand this? Okay, so not clear. Okay, so okay, so what I can do, I can use a paint or something, so to draw it maybe little bit. So let's say paint, if I can draw it. Let's say we have a slice of like this, and we have three tracks. One, two, three. Okay, and now we have, this is the transition line, sorry, and let's say these two tracks are dark, so this is dark, or brass I can use. Oh, sorry, be thicker or something. Huh, correct. So these two tracks are dark. Very crude. And here this track is dark. Uh, um, let's say pencil. This is another track. And here this track is dark. Okay. Now, due to misalignment, it may happen that instead of single transition line, the transition happen here. Okay. Instead of single transition line, the transition happen here. So if we have single transition line, what we are getting? We are getting, let's say it is rotating like this. So what we are getting, if you have a single transition line, you will be getting 0, 0, 1, 0, 0, 1, 2. What you are getting 0, 0, 1 to 1, 0, 0 if there is no misalignment. Now if we have misalignment, what we are getting? First you have 0, 0, 1. Definitely we are using the binary 0, 0, 1, and then think about this portion, this slide. So this portion, so here we have all three dark. So from there we are getting 1, 1, 1, then we are getting 1, 1, 0, 0, 0, 1, and then 1, 1, 0. Okay. So you see, due to misalignment, this is coming into picture, which is not correct if we use the binary code. Now, is that okay to all of you? Siddharth? So if we want to, so this may happen due to the construction process. And if this happens, always this some another pattern will come which is not correct. So to avoid these, we cannot perfectly avoid the construction mismatch, misalignment. But to avoid this, we have to go for binary to gray. So in gray, there will be no chance because always there will be one transition. Here there are two transitions, three transitions is happening, 0 to 1, 0 to 1, and then 1 to 0. So, but in the grayscale, always there will be one in pattern, always there will be one transition. So this type of problem will not arise at all. So it is a drastically gross error it will give. Okay. Fine. Now I think it is clear. It is a very crude drawing, but it's okay. Yes. Okay. Now we could go. So due to that, we need to go with the gray scale, not the binary. So in gray, if you see here, okay, that's what I overlooked there. So in the binary, it is the binary. So now let's go to gray. So if you see the gray scale, 3-bit gray scale, so you have 0, 0, 0, 0, 0, 1, 0, 1, 1. So you see always there is one transition. Nowhere it is more than one transition. So for that, grayscale is so important here. Hmm. And now, so the output is coming out of grayscale, and now you have always you can convert to gray to binary with this type of circuit. So this is the 4 track, and you can go with the gray to binary with this XOR. Always it is possible. So whatever output you are getting, it is in grayscale, you convert it to binary, then you give it or feed it to computer, and it will read the bit and it will say that what is the angular displacement. Okay. Is it okay to all of you? This is the basic principle. Now, so this one is the absolute displacement, absolute angular displacement. So within 0 to 360 degree, we can measure absolute angular displacement. Now, the same thing can be used as a velocity sensor. How you can use as a velocity sensor? Very simple. Now, let's again go to this figure. Instead of so many tracks, you remove all the tracks. Only you have a single track. Okay, let's say only we have the outermost track and all other tracks are removed. Now we have a single track which is opaque and transparent, opaque and transparent, opaque and transparent, and we have a single source and we have a single detector. Now single source is emitting light, single detector is absorbing light, and it is so, and this shaft is rotating. We want to know the velocity. Velocity means angular velocity, RPM or so. So only single track, it is rotating with the shaft, and then we need to know. So if it is rotating with the shaft and we have a one photo detector and we have a one light source, what will happen? So quickly the transparent and opaque will come. So we'll get output as a kind of sinusoidal output. We'll get output as a kind of sinusoidal output, and from there sinusoidal output, because it will, you are thinking that it will be square, it will never be square, because there will be no such perfect transition, because whatever focusing point and all those things you do, the light will little bit dispersed, and then velocity and the voltage at the detector will slowly rise, then it will fall. So you have a kind of sinusoidal output with the theta. So, and then you apply a Smith trigger. So if you apply a Smith trigger on kind of sinusoidal or changing, uh, you will get a square wave. Now you apply a counter. So you count the square wave, number of peak, and the time span. And you divide the number of peak by time span, you will get the velocity. So how do you calculate? So you know the velocity very well. So this can be used as a velocity sensor. So again, I am telling how this can be used as a velocity sensor. To use it as a velocity sensor, we need only a single track, not more than that. And that is consist of opaque and transparent, and only one source of light and only one detector, and light source is emitting light and detector is absorbing the light, and then giving the output voltage. As the shaft is rotating slowly, it is so very, with very rapidly, it is going to opaque and transparent, and ultimately kind of sinusoidal wave we will get output. And then we apply a Smith trigger, we will get a square wave, then we count the number of square wave for a specific time window. So we know the time for the time window, we count it, and we divide it the count by the time, we will get the velocity of the rotation. That is the way we can use the shaft encoder as a velocity sensor. Now tell me if you understood this. Okay, as you are not saying anything, I hope you understood. Now we'll move encoder mode. So one slide I just keep, this is this one. So till now, whatever we discuss, we say that it can use the angular rotation, or it can use the angular velocity, and so on. Hmm. Angular displacement, that angle theta, or it can give the angular velocity, RPM or such thing. Now you might be thinking, can this absolute encoder can be used as a uh, displacement to linear displacement device? The answer is yes, this can be used as a linear displacement device. So it is called the linear optical absolute encoder. Okay, it is called the linear optical absolute encoder. Now you see the construction, you may have many tracks. Here we assume we have one, two, three, four tracks, and you have uh, one zero line. Zero line is always dark. Okay, and you have four tracks, one, two, three, four, and here you see this is the most significant bit, half of the dark, half of the opaque, and here you have least significant bit, so it will be, so if you see, it is 0000 means 0, 0001 means 1, like that it can go, and 1111 means 15. And if you make this opaque or transparent, or you can do it, if you are thinking, you can do it as a instead of, if it is optical, it will be definitely opaque and transparent. If it is magnetic, or if it is some conducting, you can make it as a copper, and this is copper strip, no copper, copper strip, no copper, and you may have a slider on it, and in that case you can use the bulb, so that bulb will glow. Okay, according the reading you can take. So here, if you make the resolution at 0.01 inch, so you see that within the 16, so 0.01 into 16, that's been 0.16 inch you can measure. If you use more tracks, you can increase the resolution. Okay, So this can be used both as a optic. This is whatever the figure is given. It is not the optical. It is a kind of either magnetic or in conducting part is there. So that light is given. It is glowing. Okay. So linear optical absolute encoder, this principle of operation is identical with that of the angular uh, optical encoder. The only difference is that instead of angular motion, it has the linear displacement, and the encoder is a linear rectangular shape made of transparent material and instead of a disk. So it is not a disk. It is made up of transparent material, and on which etching process we can make uh, dark and transparent. And it is a kind of rectangular thing. It is not a disk, and it will not rotate. And the length of this depends on the length of this full rectangular disk is depends on that how much you want to measure maximum range, and then the resolution, based on the resolution you can divide the tracks. So if you have for more resolution you can have 10 tracks, 12 tracks, and so on. And similar to this, you might have the light source, and you might have the detector, or if you have the conducting things you can have the battery and the connecting circuits, and you can easily construct such linear optical absolute encoder. But truly speaking, if you see or if you work on any industry or if you go for higher study, both of the things are now very rare seems to you. All of you want to go some software company. So then software company you will not get flavor of it. But if you see, if you go higher study or some hardware or departmental job, you will see that the linear optical absolute encoder is very rarely used. It is not very frequently used. But this disk angular displacement and the velocity, it is very, very frequently used to any circuit. So for example, in our lab, we have a servo motor which uses control mechanism to control its angular rotation, angular displacement, as well as the velocity. In a DC motor, DC servo motor, we have the mechanism in lab. So there, whenever we use the computer and we want to measure the angular displacement and we want to take a control action out of it, we use that the optical encoder. So basically it is a shaft optical, rotary optical encoder, and you will see from the encoder a bus, means the beat of the many wires, 8 wires or 16 wires, is coming out as a bus, and it is connected with the interface of with the computer. Why it is a bus? Now you will realize that there are all the lines are coming from the bit. So one is the most significant bit, another is the least significant bit, and that is going to the computer. It is very frequent that, and it is a very, very popular device. But the linear encoder to measure the linear displacement, it is that much not popular, and it is very rarely used in real cases. Okay. Now tell me any doubt you have. Okay. So now next, where what we'll move, encoder only we are reading. So, oh, another thing I forget to mention, that is multi-turn rotary encoder. So I mentioned that the 0 to 360 degree it can measure. Now suppose you want to measure, so it is called the multi-turn absolute rotary encoder. Okay, so far what we discussed that we have discussed that the position or angular position we want to measure is within 360 degree. But what happens if we want to measure angular displacement which is more than 360 degree? In this arrangement here in the figure, you see that we can, without disturbing the earlier things, we can measure more than 360 degree. How we can do it? So just earlier mechanism we used, but we use a gear arrangement. Okay. So with the gear arrangement, you can measure any displacement above 360 degree. Okay. So this type of mechanism is called the multi-turn absolute rotary encoder, and it is available in the market with the different gear ratio and the name suggests that it can measure beyond that 0 to 360 degree. That is what multi-turn is giving. Single turn means 0 to 360. Multi-turn means more than that. Now in this figure, in the arrangement, what we made in this arrangement, there are two discs. You see the disc 1 and disc 2 is written. So disk 1 has the set of detectors and set of sources. Disk 2 also has a set of detectors and set of sources. So now disk 1 and disk 2 are connected to each other with a gear arrangement of 8 is to 1. What is the meaning of 8 is to 1? That means to rotate the disk 2 one full cycle, that means 360 degree. To rotate the disk 2 360 degree, disk 1 has to rotate 8 times. Okay. So in another words, if disk 1 rotates full 360 degree, disk 2 rotate only 45 degree. This is the kind of gear arrangement 8 is to 1. So here you can get gear arrangement 4 is to 1, you can get 2 is to 1, you can get 16 is to 1, based on at how many multi-turns you want to measure. So this type of arrangement you can do. So the first disk is connected with the second disk with the gear arrangement with the different gear ratio. Okay, in figure it is mentioned 8 is to 1. So now you see that the second disk is geared with the disk 1, and in the disk 2 also you have a source and detectors, and you will get output from the both disk 1 and disk 2. Now, if you see the disk 1 is rotating 360 and disk 2. So disk 2 you can make a 3-track into the 3-track encoder, which is 1 is to 8 ratio, and disk 1 you can have many 10 to 12 tracks. Okay. So let us give some specific numbers so that it will be more useful to understand. Let us take a specific example. Say disk 1 you have a 10 tracks and disk 2 you have a 3 tracks. So the disk 1 can rotate one, if rotates one full cycle means 360 degree, the resolution will be 360 by 2 to the power 10 or 360 by 1024. Okay. And now in the gear arrangement, you know, in the disk 2 has the 3 tracks. So you know that which track this encoder is. If it is on the first, that means it is a in between 0 to 360. If it is on the second track, the angle is in between 360 to 720, like this. So suppose the disk 2 has a 3 bit, so it has a 45-degree resolution. So if it is in the first 000 point, that means it is 0 to 45-degree location. That means the disk 1 is rotating the first time, and then if it is go 45 to 90 degree, uh, then that means disk 1 is completed one full rotation and it is going for second rotation. So by seeing the disk 2 position, you can say, you can calculate the angular rotation of disk 1 in between 0 to 360 into 8 degree. Okay, this is the way. So now tell me if you understood this. I sort of quickly complete. Hmm. Okay, velocity. Velocity encoder I can. Okay, velocity encoder I can tell again. So velocity encoder, Rajal Kumar is saying to explain it again. Definitely I'll do it. So in velocity encoder, what I was trying to say. So we have a encoder, but we don't have many tracks. We have single tracks. That I mean to say. We have single tracks, only single tracks. There is no other tracks. Okay. So that means it is a kind of this mechanism. I thought you will understand. That's why I did not give the figure. So it is a circular one and it has a single track, not more than that. And the single track is divided into many opaque and transparent. Okay, opaque and transparent, many opaque and transparent. So this might be opaque, this is transparent, this is opaque, and again this is transparent, again this is uh, opaque, this one, again this is transparent, again this is opaque, like this. Okay, so now, and it is rotating, and we have a single detector and single source. Now as it is rotating, the light is coming from the source and it is going to the detector. So suppose it is a rotating. Okay, and you have a block which is source and detector, that means photodiode. And what will be the output of it? The output of it will be, kind of sinusoidal wave, because it cannot be, this is theta and it is voltage, so it is kind of like this. Okay, because it will not be perfect square wave. Now you apply a Smith trigger on it, then how the voltage you will get? Smith trigger will give you perfect Vsat or minus Vsat. So theta versus, you will get velocity voltage V. How you will get? You will get a perfect square. Okay, I am just trying to synchronize it. Okay, and then you apply this one with a counter. What counter will measure? Counter will count that how many up latch is coming. Okay, so suppose you have 10 up latches, the counter made it. Okay, and also counter make that what is the time duration it is counting. And suppose you have a time duration t second, so 10 count in t second, so one count is 10 by t, and then from there you can calculate the voltage, calculate the angular velocity, whatever. If you want radian per second or if you want RMSE, this is a simple calculation or change of scale. This is the all about the velocity encoder. Do you understand now? Please tell me. Prujwal Kumar, please tell me if you now understood this. Okay, now this is clear. Now you all of you tell me if you understood the this shaft multi-turn, more than one turn. So all of you tell me please if you understood the multi-turn encoder. So just if, or if you have any doubt, you can just tell me that we don't understand. I can again explain. Okay, so hopefully all of you understood this, because nobody is saying anything. Just 1 minute, one sentence I am telling. It is very simple. It has only a gear arrangement. So it has two discs and gear arrangement. It may be 8 is to 1 or 12 is to 1 or 16 is to 1 or 4 is to 1, whatever. And this consists of many tracks, 10 to 12 tracks. And these discs based on the how many gear arrangement. So if it is 1 is to 8, you may have 3 track, because 2 to the power 3 is 8. If it is 2 to the power 4, 1 is to 16, you must have 4 tracks here. And if you have 1 is to 4 is to 1, you might have 2 tracks here. So here it will give the exact angular displacement, and here it will give that how many, after how many full rotation this angular displacement is happening. So from here you can suppose you have a second position, so you have 360 into 2, 720 plus the whatever the angle is coming from this one, that will be the angular displacement of the shaft. So this way we can measure the multi-turn. Okay. Okay, so now today the time is over and I took more time. Anyway, so now it is time to end. So all of you think and tell me when you want to give second viva. I am thinking about this weekend. Okay, because our exam is end sem exam is coming. So this weekend we can proceed if you like uh, for second viva this weekend. So it will be good, and uh, you all of you think and discuss, then we can decide it, no issue. Tomorrow, day after tomorrow is holiday most probably, so tomorrow I don't know. If there is no class, I will inform you. Tomorrow there might be no class, and then day after tomorrow is holiday, so people will not be there. So maybe we need 3-4 classes before the end sem. So whenever you will give 3-4 classes, I can take 2 days, 2 to 4 classes I can take, and I can finish this week only, so that you can get one more week to read. There will be no class, as you wish, or next week if you want I can also take. But I prefer to finish this by this week, so that you have 1 week time to read. So I will take 4 more classes, not more than that, and within that I will finish the syllabus, and then you will go for the exam. Okay.
Sir, what will be the syllabus for the quiz, for the
All,
Viva?
all, beginning
For,
to the End. End means
Sir, is it possible to take a quiz for a short period of time? Because, sir, many of the students,
short period means.
uh,
Please mention, Akanksha, what is the
so,
meaning? Short period.
short period means 20 minutes to 30 minutes, like, so because many of the students said that they at the night it is difficult to give the quiz because it took the whole day. We couldn't study for the whole day.
Oh, so
And
night it
sir,
is difficult. Then what you propose?
sir, all of the students suggested that if it is possible to take a quiz for a short period of like to 20 to 30 minutes, that would be good instead of a
Short period
viva
means
because it took
students.
3 days.
Just 1 minute. Short
Yes.
period means 5 minutes. You are saying.
No, sir, 5 minutes is very less. Like, if there will be 10 to 15 questions, like, we need 20 to 25 minutes.
That's what I was going. Not more than 20 minutes. I went. I
Like, sir, if
planned 10 minutes. It went 20 minutes.
yes, sir.
Actually, I said that each student must be giving Viva for 10 minutes. But it went to 20 minutes.
Yes, sir.
So that is the problem you mean to say?
No, sir. It's
Then
not.
where is
I'm
the
not saying this, sir. I'm saying like the Viva took around 3 days. So, sir, all of us are saying like we couldn't study other subjects at that time. The roll numbers like at the last, and the roll numbers who give their Viva at
Yeah,
the
so
night.
then you propose na what I can do.
So,
75 students, if
sir,
I take 10-15 minutes, how many hours it is coming? So what I can do? You suggest something.
sir, we
Quiz
are saying like if you can take quiz, we are not just
quiz means
forcing this.
open
Quiz,
book,
quiz.
open WhatsApp, quick, come and write by copying.
It depends on the student if they are copying. Like all
Everybody
are
copies.
not copying.
Everybody copies. You people are not trustworthy. Everybody copies. Most
Okay,
of
sir.
most of you. So
Okay.
you propose some mechanism so that it cannot go for 3 days. I will be happy, more than happy. 3 days also I don't want. 3 full days I am spending, right? So
Yes,
if you
sir.
can propose within one day, I will be very happy. But no written quiz. So you will copy to each other.
Okay, sir.
So you propose something which is not copyable and which will take less time. I will be happy to follow that path. Okay.
Oh, okay, sir.
Okay. Thank you. So now we can end here. Hmm. So tomorrow most probably there will be no class, but I am trying to finish this week, and I have 4 more classes. Then the syllabus will be finished. Okay. Thank you for all of you to join. Now you can leave. We end the class here, and